We do not know the Milky Way galaxy. Yes, even though we are in it. Before you think I'm talking about niche details about stellar formation, how galaxies evolve or things like that, I'm not. Even some of the basics about the Milky Way are mysteries to us, like how many stars are here? What is its basic shape? Specifically, does its spiral have 2 arms or 4? Although those might seem like simple details, we don't actually know them. Number of stars estimates range from 100 billion to as high as 400 billion, depending on what estimates are being used. Scientists have gone back and forth between 2 or 4 arms over the last 2 decades, and currently we're leaning towards 4. This makes sense. It's naturally harder to look at a thing that you're inside. It's easier to look out your window at the house across the street than it is to look at your own house from that same position. But here's a fun one for you. How many galaxies are in the Milky Way galaxy? According to ESA's Gaia Space Telescope, which just finished its 10-year mission, the answer is not just one. Gaia has been mapping the stars of the Milky Way, performing 3 trillion observations. And now, as it takes its final look at our galaxy, the data is being evaluated. 30,000 stars are moving a little strangely. They are going the wrong way. They are originally not from around here. I'm Alex McColgan and you're watching Astrum. Join me today on a deep dive into Gaia's data to answer exactly how many galaxies did the Milky Way eat. As I already alluded to, looking at our own galaxy is surprisingly hard. I've mentioned before in a previous video how all of the stars, stellar clouds and gas can actually get in the way of what we're trying to look at. This gets particularly bad towards the center of the Milky Way's plane, where the most matter accumulates, creating an area astronomers refer to as the zone of avoidance. Visible light cannot easily penetrate this zone, leading scientists to resort to other mediums like X-rays to scrutinize what lies beyond. To carry on our house analogy from earlier, we are sitting in our bedroom, trying to figure out the layout of the rest of the house, but the walls right in front of us are preventing us from seeing any of the other walls and rooms. Further compounding this is the difficulty in telling how far away a star is from Earth. To make an accurate 3D map of the Milky Way galaxy, you need to know if the stars you can see are dim, small, close ones, or large, bright, distant ones that only look dim and small because of their distance. Not all stars make this easy. While some type of stars, such as Cepheid variable stars, have a predictable enough luminosity that their distance can be calculated if you know a few things about them, not all are quite as accommodating. So, for unpredictable stars, how can you tell how far away they are? The answer is parallax, and that's what Gaia has been using over the last 10 years for its galaxy map. Parallax is the principle that, depending on your point of view, things can appear to be in different places. You can see an example of this right now by holding up your finger in front of your face. Close one eye, then instead close the other. Now alternate quickly between the two. See? Your finger moves quite significantly in relation to its background. The closer an object is, the greater the effect of parallax. Simple trigonometry takes care of the rest, allowing you to calculate how far away an object is. While this effect was very noticeable based on a finger in front of your face, you'll see much less parallax on a tree on the other side of a field, which means it's further from you. The further away something is, the harder it is to use parallax to tell you its distance. Things can get a little imprecise. But how then can we use this method to calculate the distance to a star? The secret is to widen your base viewpoint. Just as the distance between your eyes can influence the effect of parallax on an object, Gaia viewed stars not just once, but multiple times over the course of a decade. In that time, the face of our night sky will have changed, as we can see in time lapses like this one, with an exaggeration of 10,000 times. Rather than using the 6 centimeters between your eyes as the base, every half year we can make the solar system our base instead. Our Earth moves from one side of the Sun to the other, which causes parallax effects to be visible in every star we see. Note how in this animation the stars are taking little looping patterns? That's not really how they're moving, but how we are. That's the effect of our own loops around the Sun. This can help with measuring stars' distance, but there's actually an even larger scale we can use: the proper motion of stars. We can ignore the loops for this one, as an even larger base is coming into play. Rather than just use the motion of our planet on either side of the solar system, we can make use of the fact that our own solar system, along with the other stars in the galaxy, are also moving. So we can use that motion as an even larger base for establishing parallax. The same principle applies. Stars with proper motions against the backdrop of space are closer, while stars with less proper motion are further away. In this way, Gaia has been building a precise 3D map of 2 billion stars in our Milky Way galaxy and beyond over the course of 3 trillion observations. But Gaia has not just been looking at their motion and distance. ESA's mission for this telescope was to study the luminosity, temperature, mass, and chemical composition of these stars too. It houses 2 powerful telescopes that channel light from 2 different directions into a camera with nearly 1 billion pixels, the most precise camera in space. Its radial velocity spectrometer can measure Doppler shift to give us clues about its velocity. It also has photometric instruments to reveal spectral information about each star's properties like composition and temperature. So, although 2 billion stars is only a drop in the ocean of the 100 billion stars thought to inhabit the Milky Way, this still allows us to create an incredibly detailed map of our galaxy over time. And it's that over time bit that allows us to see the Milky Way's eating habits. Since 2013, when Gaia was launched, it has been collecting data which ESA scientists have been processing and releasing in large data packets for the general scientific community to study. The larger the gap in time, the more comprehensive and precise the data. More time equals more parallax. 3 such data releases have taken place so far, in 2016, 2018, and a 2-parter that released a simplified version in 2020 and then the full version in 2022. And scientists have already had the chance to evaluate what Gaia has seen. And as they witnessed the motions and locations of stars in our galaxy over time, it became possible to model the whole galaxy and even wind it backwards. Take a look at this. It's impossible to photograph our own galaxy, as no camera-equipped spacecraft has traveled out that far. But here is a representation, created using Gaia's data, of what it looks like, to an unprecedented degree of accuracy. Note its wobbly edges. These indicated to scientists that the Milky Way crashed into another galaxy in the distant past. Using the second data release, researchers from the Netherlands looked at 7 million stars and found that 30,000 of them were moving strangely. While most stars, including our own, move around the Milky Way in one direction, this odd collection was moving the opposite way. Their color and brightness were also strangely distinct, indicating there was something special about this particular group. The researchers ran the numbers and found that a model that fitted their observations was what would happen if another galaxy collided with our own. The collision must have happened 8 to 11 billion years ago and involved a small dwarf galaxy that the researchers called Gaia Enceladus, or sometimes the Gaia Enceladus sausage. See how its stars, indicated here in red, actually managed to retain a fairly discrete form for a time, before eventually spreading out across the Milky Way. This merger may have been an important part of how our Milky Way came to have some of its unique characteristics, such as a bar in the center, something that only 2/3 of spiral galaxies have. The Milky Way didn't go in for a little late-night sausage eating just once though. Another dwarf galaxy, known as Aruya Sequoia Litoi, was also found to have merged with the Milky Way, and perhaps was a binary pairing with Gaia and Enceladus. And then, in a later study, another dwarf galaxy's remnants were found. More than one, in fact. According to this study, our Milky Way may have eaten as many as 6 other galaxies. Gaia data reveals this hasn't stopped. The nearby dwarf galaxy Sagittarius has collided with our own 3 times already in the past 4 to 5 billion years, and is set to do so again. This collision may have even been the spark that lit the flame of our very own Sun, which came into being around that same time. Eventually, Sagittarius may well become galaxy number 7 that the Milky Way has consumed, all of its stars being slowly ripped away and brought into our own galaxy. These revelations are just some of the incredible discoveries made possible through the Gaia telescope's data, which is why it is sad that Gaia's time has come to a close. The Gaia telescope maintained its position in the second Lagrange point using judiciously applied cold gas propellant, 12 grams a day. However, that cold gas has finally run out. On the 15th of January, Gaia took its last observation and has begun the process of doing a few last calibrations before finally powering down on the 27th of March 2025. But its story is not over yet. 2 more data packets await release. The first of the 2, Data Release 4, will include 500 terabytes of information and will be released in 2026. It will only cover the first 5.5 years of Gaia's mission, but will do so to an incredible level of detail. Its precise measurements of stars' wobbling motions might even highlight possible locations of exoplanets, and will create the largest catalogue of binary stars to date. It's also worth recognizing that the discoveries Gaia brought us don't end with just prior or ongoing galaxy impacts. It's possible to fast forward the data to model the motion of our local stars millions of years into the future, allowing us to see incredible models like this one. Note how, although the stars near us initially spread out across the Milky Way, they later reconvene due to what is thought to be density waves. Seeing this play out helps explain the spiral arm shape of our galaxy. Gaia data has helped improve our picture of events much closer to home too. Gaia revealed the position and direction of travel of over 150,000 asteroids in our solar system, and thanks to its ability to track those movements over time, Gaia was able to demonstrate that 352 of them probably have moons, as shown by slight wobbles in these asteroids' trajectories. This nearly doubles the number of such binary system asteroids that we are aware of. Gaia has been called a treasure trove, and it's hard to overstate just how much information can be found in these data releases. Gaia has provided us with the largest ever 3D map of quasars across the wider universe, identifying 1.3 million of them, with the earliest being spotted at the edges of the universe, with light that started traveling when the universe was only 1.5 billion years old. Gaia has found a previously unknown black hole in our Milky Way, 33 times the mass of the Sun, and only 2,000 light years away from us. This type of black hole had never been seen in our galaxy before. Most local black holes are only 10 times the mass of the Sun, making this new find truly massive. Many more such discoveries can be found thanks to Gaia data. It's no surprise that ESA is already considering plans for a Gaia replacement, Gaia NIR, a space telescope similar to Gaia, but able to see much further into the infrared to peer through the gas clouds that obscured Gaia's vision. But don't hold your breath for this one. If it goes ahead, Gaia NIR will look to launch in 2045 to provide an approximate gap between that mission and Gaia, to allow ESA to take even more advantage of parallax effects. Gaia NIR will be able to see how much further Gaia's observed stars have travelled in the intervening time. When it comes out, Data 5 will be the big one. Tentatively set to be released by the end of the decade, this data release will include everything, all 10.5 years of Gaia's mission, to the highest level of detail imaginable. It will truly be a treasure trove of information. Just think what discoveries can be made with so much raw data to sift through. Who knows what else we will learn about our galaxy. So, while Gaia's mission coming to a close is sad, the wealth of data it has collected is also very exciting. Our Milky Way galaxy might be surprisingly hard to learn about, but Gaia's data will give us the best crack at it to date. We've all seen pictures of galaxies, often glorious objects with spectacular colours and shapes. However, because they are static images, it may make you wonder how they rotate. The first obvious thought is that they spin around an axis, perhaps looking something like this as they do so. Would it surprise you to hear that this is totally wrong? For a start, galaxies are not solid objects, but rather made up of millions to trillions of stars. Each star follows their own orbit, although they are often going in the same direction at least. But actually, one of the main reasons a spiral galaxy does not orbit like the first example is that angular momentum would wind the arms up into tighter and tighter spirals. We don't see this, so something else is at play. The leading theory is that these arms are caused by density waves, meaning a galaxy's rotation would in fact look like this. Here the arms stay in place, or at least move extremely slowly as stars and gas pass through them. Another theory is that shock waves produced by supernova and stellar winds are the cause of the arms. These theories might not be mutually exclusive, and both processes may be at work here. Density waves are potentially caused by the self-gravity of stars as they orbit after they have been perturbed by another force. As stars have a gravitational influence on each other, eventually a pattern forms where their orbits meet around certain areas in the galaxy. Very, very interestingly, density waves are even seen in certain parts of Saturn's rings. Here you have a section of ring that appears like the inside of a tree trunk, but this is not the case. In this region, the ring is influenced by the gravity of small Sheppard moons tucked inside the rings. What you are actually looking at is one very tightly wound ring, a bit like an LP record. And just like with a galaxy, this arm stays the same shape, never getting tighter or looser. Within these arms is where the majority of star formation takes place in a spiral galaxy. The gas and dust within a galaxy clump up in these arms too, which is why you often see star-forming nebula dotting the arms. The arms are also brighter, not just because there are more stars here, but also because all the hot, young, bright stars are found in these regions. Because the hottest types of stars are so short-lived, by the time they move away from the arms, a lot of them will have already burned out. Another interesting phenomenon to do with spiral galaxies is something caused by dark matter. In the early universe, when dark matter was more dispersed, stars within galaxies that are dominated by normal matter would orbit a lot slower around the outside of the galaxy than towards the center. However, today, stars are moving a lot faster near the edge of the galaxy thanks to the influence of dark matter. Dark matter is mysterious in that it cannot be seen or observed in any way other than by its gravitational influence. Dark matter seems to have clumped towards the center of galaxies over time, making stars orbit faster than they should around the edge of a galaxy if only gravity from normal matter was accounted for. Other theories also exist about why this may take place, but these would have to change the way we currently understand physics. Anyway, how do we know about this change in the way stars orbit galaxies? Well, of course, we can see back in time when we look at extremely distant objects. Stars within galaxies billions of light years away seem to orbit slower than stars much closer to us, and this effect scales depending on the distance to the galaxy. Of course though, there are some rule breakers out there. While most galaxies have stars that orbit like this, a few have been spotted that have leading outer arms. One example is NGC 4622, a bizarre galaxy that rotates in the direction the arms are pointing. This was hard to accept at first, until smaller inner arms were also found. This unusual galaxy has probably experienced a merger in its not too distant past, which likely caused this phenomenon. Another rule breaker is the Black Eye galaxy, which has two counter-rotating disks of gas and dust. The inner disk, where you can see all the dust lanes, rotates normally, whereas gas in this outer disk rotates the opposite direction. Interestingly, stars in this outer region do not seem to be orbiting retrograde, meaning it is just the gas that does so. It is believed that gas must be still getting fed into the galaxy from the intergalactic medium, or that this galaxy also merged with another extremely gas-rich galaxy. The last thing I wanted to show you today is the other major category of galaxy, elliptical galaxies. Elliptical galaxies contain stars that are generally much older than those found in spiral galaxies because the dust lanes in these galaxies have been exhausted, meaning stellar production has all but stopped. In these kind of galaxies, stars are very much independent from each other, following their own rather elliptical orbits. Sometimes galaxies can exhibit characteristics of both types of galaxies. These are known as lenticular galaxies. These galaxies have dust rings which haven't fully been exhausted yet, and they have quite a ghostly appearance. Star formation does appear to be a factor in keeping spiral arms defined, as once the stellar building blocks dry up, we've seen examples of spiral galaxies losing their definition. Perhaps lenticular galaxies are the midway point between spiral galaxies and elliptical galaxies. So there we have it, a look at how galaxies rotate. The universe is full of secrets, and some of the most incredible ones are hiding just beyond the reach of visible light. What if I told you that more than 1.5 billion unseen objects, from galaxies and newborn stars to some of the oldest stars in our entire galaxy, are sitting just out of reach of us, cloaked in cosmic dust? That's a little frustrating to think about, isn't it? Until now, that is. Because thanks to the European Southern Observatory's Visible and Infrared Survey Telescope for Astronomy, better known as VISTA, we can finally lift the veil on these hidden wonders. For the first time in human history, we have a pretty comprehensive infrared map of the Milky Way, one that pierces through the obscuring fog of space to reveal an unprecedented view of our galaxy and what lies beyond. I'm McColgan and you're watching Astrum. Join me today as we appreciate how this first of its kind map was made and take a look at some stunning images that reveal previously unknown stars across our galaxy. In September 2024, VISTA published the largest and most detailed infrared survey of the Milky Way ever undertaken. Encompassing a 13-year period from 2010 to 2023 across 140 nights of observation, this project has captured around 200,000 images and generated 500 terabytes of data. That's the same amount of data as it would take to stream a 4K video for nearly 3 years straight. VISTA is part of ESO's Paranal Observatory located in Chile, with its main focus being to map large areas of the sky. Using VISTA's infrared camera, known as VIRCam, the team was able to peer through the dust and gas that permeates our galaxy and uncover some of the Milky Way's most hidden places. Traditional telescopes allow us to view space in visible wavelengths, which range between about 380 to 700 nanometers. But VISTA isn't like traditional telescopes. Instead of relying on visible light alone, VISTA operates at infrared wavelengths between 900 and 1200 nanometers, allowing it to detect otherwise invisible objects like stars obscured by dust and cold brown dwarfs, also known as failed stars, which don't emit enough visible light to be seen with a traditional telescope. To get an idea of the difference between visible and infrared light, take a look at these two images of the Lobster Nebula, or NGC 6357, one taken in visible light and the other with VISTA's telescope. We can see that in the infrared, the dust that obscures our field of view seems to disappear, revealing what look like hundreds of thousands, or maybe even millions, of previously invisible stars. The map was created through VISTA variables in the Via Láctea, or VVV survey, Via Láctea being the Latin name for the Milky Way, and its companion project, the VVV Extended Survey, or VVVX. The data collected from these two companion projects that make up the VISTA Infrared Survey have already led to the publication of more than 300 scientific articles. Unlike other recent space maps, this is one of the most detailed ones ever made. It's the first infrared survey to cover nearly 80% of the Milky Way's luminous mass, and provides the largest infrared catalogue ever made of our galaxy's central region. It allows astronomers to study our galaxy in finer detail than ever before. This survey gives us an accurate 3D view of the inner regions of the Milky Way, which were previously hidden by dust. It covers an area of the sky equivalent to 8,600 full moons, and contains about 10 times more objects than any previously published infrared map from 2012. Our Milky Way consists of a central bulge, a dense, bright, puffed-up collection of stars, with a flat disk of 2 spiral arms wrapping from the ends. This image shows the area of our galaxy that was mapped in the survey. The red squares mark the central regions of the galaxy, which were observed by the original survey, and then reobserved again by the extended survey. And the other square colors show areas that were only observed as part of the extended survey. From this image, you can see that these surveys have focused right on the central plane of our galaxy, spanning part of the disk and most of the nuclear bulge. But what has VISTA revealed? Argentinian astrophysicist Dante Miniti, who led the survey project, said, "We've made so many discoveries, we have changed the view of our galaxy forever." And as much as I'd love to talk about all of them in this video, it's probably best I stick to some of the highlights. As part of the survey in 2015, VISTA turned its attention to the star formation region of Messier 20, also known as the Trifid Nebula, which lies about 9,000 light-years from Earth. Viewed in visible light in this image, we can see a beautiful nebula, glowing pink from the emission of ionized hydrogen, and surrounded by a blue haze of scattered light from young, hot stars. The cloud of gas and dust is obscuring the star-filled space behind it. Now, look at this second image taken by VISTA's infrared camera. Peering beyond the clouds reveals a whole swarm of new stars. This image not only allows us to see through the Trifid Nebula, but by chance, it revealed objects on the far side of our galaxy that had never been seen before. To their surprise, astronomers identified two faint, reddened objects as Cepheid variable stars. While they appear in the image to be just behind the edge of the Trifid Nebula, in reality they are very distant, about 7 times farther than the nebula that once helped to block them from our view. Cepheid variables are a type of bright star that is unstable. They brighten and fade over a period of a few days or a few months, depending on their brightness. The first variable star we ever identified in modern times was Omicron Ceti, also known as Mira. It had been described as a nova until 1638, when Johannes Halwoods observed it getting brighter and dimmer in a cycle that lasted 11 months. As for this pair of newly discovered stars, they are the only Cepheid variables that we have identified so far in this location, which lies beyond the central bulge on the far side of our galaxy. And they can be really useful too. You can think of them as a kind of cosmic yardstick that can be used up to distances of tens of millions of light years. If you know how long the star's pulsation period from bright to dim is, then you can infer its absolute brightness as well as its age. You can compare absolute brightness to the apparent brightness, that is, the amount of light that reaches Earth, so you have a measure of how distant the star is. With a few reference points like these, we can build up a real picture of the scale of our galaxy and beyond. Looking toward the galactic center, a team of astronomers and data scientists found even more candidate Cepheid stars, 655 in fact. They then sorted these into one of 2 classes, and found that 35 of these 655 stars were classical Cepheids, the younger of the 2. This was really exciting, especially since the galactic bulge was thought to contain mostly elderly stars that are at least 8 billion years old. Recording their pulsation periods, the team revealed that all 35 of these Cepheids were less than 100 million years old, and some of them may be as young as 25 million years old. To put that in context, our own sun is about 4.5 billion years old, so the youngest Cepheid has only been around for 0.6% of our sun's lifespan. The team's exploration of Cepheids culminated in another major discovery. By mapping the 35 classical Cepheids they found, the team was able to trace a completely new feature in the Milky Way, a thin disk of young stars that stretches right across the galactic bulge. Buried behind thick clouds, it had remained unknown in all previous surveys of the region. In revealing this structure, combined with the discovery of older Cepheids as I mentioned earlier, scientists have inferred that there has been continuous star formation along the midplane of the galaxy for the past 100 million years. There might also be even younger Cepheids that we haven't seen yet, as these stars would be so bright that they would be saturated in the VVV survey. The fact that we found this thin disk of young stars within the galactic bulge is incredible. We used to think that the galactic bulge was an ancient feature of our galaxy's past, where exclusively old stars had formed separately from the stellar disk. But this finding reveals that things aren't so black and white, and that the formation of newer stars within the bulge could be a natural progression of our galaxy's evolution. But even more inspiring perhaps is a discovery by the Vista infrared survey that lies at the ancient heart of our Milky Way galaxy. In 2016, for the first time, a type of ancient star known as RR Lyrae, another variable star, was discovered in the center of the Milky Way galaxy by a team led by astrophysicist Dante Meniti and Rodrigo Contreras Ramos. This type of star is usually found in globular clusters, which tend to orbit the outer regions of the galaxy. A globular cluster is a tightly packed group of stars that contains tens of thousands to millions of stars bound together by gravity. They're also really ancient, containing a stellar population that can be over 10 billion years old. The team found 12 RR Lyrae stars during the VVV survey, which suggests that they might be the remnants of an ancient globular cluster right at the heart of our galaxy. This finding also provides evidence that might help astronomers to decide between the two competing theories of how nuclear bulges form. While some scientists think that the nuclear bulge forms early in the galaxy's evolution, when multiple smaller galaxies violently collide, others say that it forms gradually over time, where gas is funneled inwards to trigger star formation. Finding these ancient stars here suggests that the bulging center of the Milky Way likely grew through the merging of primordial globular clusters, therefore supporting the first theory. So not only does it hint at our own galaxy's beginnings, but it also offers compelling evidence into how these galactic bulges might form in other similar galaxies. Speaking of ancient stars, Vista was able to find 2 new globular clusters as part of the infrared survey in 2011. In this visible light image, a known globular cluster, UKS-1, can be seen on the right as a hazy red splotch. This cluster had been the dimmest known globular cluster until the new discoveries. Now, compare this same patch of sky, but this time in Vista's infrared light. Suddenly, we can see what we have been missing. Much more faint than the known UKS-1, we can make out a second globular cluster, this time in the upper left of the image, which has been named VVV-CL001. Another globular cluster, aptly named VVV-CL002, was found soon after, and this small, faint group of stars may be the closest known globular cluster to the center of the Milky Way. Did you know that there were only 158 known globular clusters in the Milky Way before these new ones were found by Vista? For the survey to identify 2 more of these rare stellar objects is quite a significant accomplishment. Within this central region of the galaxy, it's easy for younger stars and cosmic dust to obscure globular clusters, especially since their age prevents them from shining as brightly. But now that they've been revealed, these features bring exciting possibilities for further study. It could just be an illusion of perspective, but scientists have wondered whether VVV-CL001 is gravitationally bound to UKS-1. If this is the case, then they would be the Milky Way's first known binary globular cluster pair. We found binary clusters in other galaxies, like in Centaurus A and the Large Magellanic Cloud, but scientists think it might be when these gravitationally bound clusters collide that we get the most massive globular clusters, like Omega Centauri. So studying a binary cluster right in our own galaxy could produce some amazing insights into this process. It's all speculation at the moment, but it's definitely cool to think about. In addition to globular clusters, the Vista infrared survey identified a multitude of other types of star clusters. At least 96 new open or galactic clusters have been found, which typically contain fewer, younger stars and are much more common than the globular type. Like the globular clusters, they have been hidden by cosmic dust, but Vista's 4.1 meter infrared telescope has lifted the curtain to show them in all their glory. Take a look at just a few of these stunning images we now have of these objects. One of these open clusters, VVV-CL003, is much more difficult to make out in images compared to the tightly packed globular clusters. Try and see the density differences in the stars in this section of the image compared to the surrounding regions. It was found by Vista 15,000 light years beyond the Milky Way center, and also happens to be the first of its kind to be discovered on the far side of the galaxy. The sheer scale of this survey is staggering. Covering a vast region of the sky and mapping more than 1.5 billion objects, this data has already led to fascinating discoveries that are rewriting our understanding of the Milky Way and beyond. And that's just the tip of the iceberg. This survey will serve as a foundation for future telescopes and observations, which will hopefully be able to expand on VISTA's legacy with even higher resolution and sensitivity. We now have the most detailed 3D map that has ever been made of the Milky Way structure and objects, one that unveiled hidden wonders previously beyond our reach, and scientists are already uncovering new galactic features and reshaping our understanding of the galaxy. With the information from this groundbreaking infrared survey, as well as the recent work from ESA's Gaia mission in visible light, it's an exciting time to be an astronomer, and we can expect a flurry of new insights about our own galaxy and the universe as a whole. VISTA's infrared observations have unveiled dozens of hidden star clusters and millions of previously unseen stars. They have revealed new stellar nurseries where stars are born, and they have broadened our understanding of the formation of our Milky Way. Looking at the sky through different wavelengths has brought about a new era of galactic exploration, and I can't wait to see what else astronomers and data scientists are going to uncover thanks to VISTA's 3D map. Have a look at this beautiful image captured by the James Webb Space Telescope. Immediately you'll notice two types of objects. First, you'll see the nearby stars within our own Milky Way galaxy, which look like points of light surrounded by diffraction spikes. But further in the background, you'll see entirely new galaxies, each containing billions of stars smeared out into elliptical or spiraling blurs. What you probably won't see are distinct, individual objects within those other galaxies, as they are far too distant and blend in with all the other sources of light. But there is one exception to that rule. One type of object that is so bright you can make it out from billions of light years away. So bright that it stands out from all the surrounding stars in its galaxy. A quasar. But what if I told you that a whole bunch of tiny quasars were hiding in plain sight, right within our own Milky Way? How can that be when they are some of the brightest objects in the universe? In this video, we'll get to see how that's possible and how a team of scientists used images of just one nearby microquasar to gain a deeper perspective into the inner workings of quasars all over the universe. I'm Alex McColgan, and you're watching Astrum. Join me today as we unravel the story of these astronomical lighthouses, one cosmic photon at a time. Astronomers have been pointing their telescopes up at the night sky for centuries. Yet, it was only in the 1950s that they set out on a quest to map out what the universe around us looks like in radio waves, rather than visible light. Think of this as the astronomer's version of putting on night vision goggles. At first, they didn't see anything out of the ordinary. Many of the same galaxies that emitted visible light also emitted radio waves, so they could be seen with or without the goggles. But then, among the stars and galaxies that were known to populate the night sky, astronomers saw something new, something that shone very brightly in radio waves, but had never before been seen in visible light. And there wasn't just one of these objects. By 1960, observations quickly grew until hundreds of mysterious radio sources had been recorded across our sky. At the time, astronomers didn't have a clue what the origin of these radio waves could be. For all they knew, the waves could come from a giant intergalactic network of alien radios. But what they did learn from follow-up observations using more precise telescopes like the Hale telescope is that you could see these objects in the visible part of the spectrum. They were just extremely small and faint. They were far too small to be galaxies. They appeared as points, not smeared out blobs in the sky, but they also couldn't be regular stars, because regular stars don't typically emit much energy at all in radio waves. For this reason, these mysterious objects came to be known as quasi-stellar radio sources, which quite literally translates to something like a star, but not a star, that emits a lot of radio waves. That name eventually got shortened to something that was a little bit more palatable: quasars. Even with the catchy name, it took astronomers and physicists nearly 30 years to really pin down what these quasars were. And unfortunately, it's probably not alien radios, although the real answer is still extremely fascinating. It turns out that the explanation centers around black holes, and not just ordinary black holes, but supermassive black holes that can be millions or even billions of times the mass of the Sun. Such supermassive black holes are frequently found at the center of large galaxies, and although black holes can't emit any light themselves, they can make quite the spectacle out of the accretion disks orbiting around them. If you want all the details, you can queue up our older video on quasars here, but for now let me just give you a quick summary. Matter orbiting a black hole can spiral inward as it loses energy due to internal friction. Much of that energy ultimately gets converted into light that streams outward from the black hole, but in some cases, the accretion disk also splits out relativistic jets of ionized matter, collimated by powerful magnetic fields along with the spin of the black hole and its surroundings. The particles in these jets can propagate through the universe from galaxy to galaxy as cosmic rays, sending out radio signals as they're pushed around by intergalactic magnetic fields. Overall, quasars emit so much energy that a single quasar in a distant galaxy will outshine the other hundreds of billions of stars in that galaxy combined. That's why, when quasars were first observed, they appeared as small as a star, but far brighter than any star outside of the Milky Way could have ever been. Now, the Milky Way has its own supermassive black hole right in its center too, called Sagittarius A star. But for better or for worse, the accretion disk around our black hole is too thin and faint to call it anything close to a quasar, and until something dramatic happens, like the collision with the Andromeda Galaxy that's scheduled for a few billion years in the future, Sagittarius A star will likely remain calm and mellow. On one hand, we're kind of lucky, because a quasar that close to Earth would emit enough high-energy radiation to be potentially fatal to terrestrial life, which makes you wonder about the kinds of life that could arise in galaxies that do contain quasars. But on the other hand, we're missing out on a second source of light in the sky, illuminating our planet almost as brightly as the Sun, and it would be so cool to get to study a quasar from up close. So can you imagine my surprise when I learned that we might actually have the best of both worlds? Quasars, alive and active in the Milky Way, and yet not so powerful as to wipe out our entire biosphere. How could this be possible? If the one supermassive black hole at the center of our galaxy isn't a quasar, then where could they be? It took a couple of decades, but scientists eventually discovered that quasars can form around ordinary black holes too, not just supermassive ones. These ordinary black holes, just a few times more massive than the Sun, typically form when giant stars collapse, so there are loads of them spread throughout practically any galaxy. You probably wouldn't expect one of these black holes to have its own accretion disk, but once in a while, a nearby orbiting star might get sucked into its gravitational pull and act as a source for the smaller, less deadly version of a quasar, a microquasar. Even though the jets of a microquasar are much weaker, they can be easier to study because of their proximity to Earth, allowing us to learn more details about the properties and dynamics of both microquasars and their larger, full-scale counterparts. The very first microquasar was discovered in 1979 and was given the obvious name SS433, as it was originally documented as the 433rd entry in a catalogue of stars compiled by astronomers Nicholas Sanderlich and Bruce Stevenson 2 years prior. To date, only a handful of microquasars have ever been found, and SS433 in particular has been a subject of widespread wonder and research. Despite its name, SS433 is more than just some ordinary star in a catalogue. It is a Type A supergiant orbiting around a stellar mass black hole in a binary system. As the black hole accretes material from the supergiant star, it produces a pair of jets perpendicular to the line of sight from Earth, meaning that the jets themselves will never actually hit us or reach our detectors. But as the jets propagate outward, they emit light in all sorts of directions, allowing us to image them at various wavelengths and learn more about how they are produced. One of the first things we saw was that there are actually two types of jets emanating from SS433. The inner jets extend out just a couple of light years from the black hole before fading away, while the outer jets appear 75 light years out and span an additional 300 light years or so. We still don't know how exactly these outer jets form, or why they terminate after 300 light years, and we only have a rough idea of what they're even made of. But a recent study from the HESS collaboration gave us some new clues to answer these questions. One such clue is the presence and distribution of high-energy photons, called gamma rays, being emitted by SS433. Ordinarily, stars or accretion disks could not be expected to produce any gamma rays because their temperatures are far too low. But the outer jets coming out of SS433 seem to emit them in spades. What's even more surprising is that even though the outer jets are extremely hot, the spectrum of light that they're emitting isn't consistent with an ordinary thermal distribution of photons. So, what's generating all of those gamma rays? The current theory is that the outer jets contain high-energy electrons that can bump into lower-energy photons passing through the system, and they transfer their energies to the photons during those collisions. This process goes by the name of inverse Compton scattering. The scientists at HESS realized that measuring the energy in these emitted gamma rays can give us a lot of information about the energy of the electrons in the jets that produced them in the first place. And what they found was in full support of the inverse Compton scattering theory. The highest energy gamma rays, carrying over 10 tera electron volts of energy per photon, or about 10 trillion times more energy than a photon of visible light, were primarily coming from the innermost region of the outer jets. Gamma rays with lower energies, on the other hand, came from correspondingly farther distances down the jets of S433. This distribution is a clear indication that electrons farther down the jets have less energy to transfer to photons than electrons right at the beginning. Or in other words, as the electrons stream along the outer jets, they tend to lose energy over time, presumably due to their collisions with photons. But how did the electrons acquire such large energies to begin with? Models suggest that their initial launch velocity from the black hole was just about 1/4 of the speed of light, but by the time they reached the outer jets, these high-energy electrons appear to be moving at speeds greater than 99% the speed of light, multiplying their initial energies by a factor of 1 billion. The HESS collaboration believes that this wild acceleration occurs due to a shock wave at the base of the outer jets caused by complicated configurations of magnetic fields. Each time an electron interacts with the shock front, it gains a boost of speed as if it crossed a boost pad in Mario Kart. And due to the diffusion of electrons back and forth within the jet, some electrons can cross over this boost pad over and over and over again, like an infinite speed glitch. This process is called diffusive shock acceleration, and it may be responsible for amping up electrons to energies in the hundreds of tera electron volts, just enough to be able to produce the high energy gamma rays observed by HESS. But shedding light on the production of photons within the outer jets of SS433 is just the beginning. Microquasars scattered throughout the Milky Way can hold treasure troves of information about the inner workings of even the most massive quasars in the center of distant galaxies. And now that we know to look for them, microquasars are less like hidden gems and more like beacons in the sky, posing for our astronomers to capture their beauty in an entire spectrum of photographs and revealing ever more shocking surprises. So, what surprised you from today's video? Was it the possibility of shockwaves in deep space near black holes? Or was it the fact that the Milky Way is home to dozens of little quasars of its own? Let us know your thoughts in the comments below. Black holes are the densest objects in existence, with gravity so powerful that even light can't escape. As such, it comes as no surprise to find the largest black holes at the center of galaxies, where matter has been fed into them for billions of years, continually increase their mass. The very largest of these supermassive black holes can be billions of times the mass of our Sun. However, it may come as a surprise to you to realize that some of the most massive black holes we know of are actually the youngest. You see, when we look at distant galaxies, we are also looking back in time, and the galaxies billions of light years away often have the largest black holes. If the universe is only 13.8 billion years old, and light takes billions of years to reach us, that means the galaxy we are observing can only be a few billion years old at most from our perspective. Pretty young for a galaxy. Surely though, it should be the case that nearer and thus older supermassive black holes are more massive, seeing as they've had so much extra time to consume matter falling into them. So what's going on here? The very largest supermassive black hole we know of is known as TON 618, with an incredible mass of 66 billion solar masses. By itself, its mass is comparable to the Milky Way galaxy. However, TON 618 is exceptionally far away, and it's taking light emitted by it 10.8 billion years to reach us, meaning we are observing it as it was 10.8 billion years ago. This means it can be at most around 2.8 billion years old. By comparison, our own Milky Way galaxy is approximately 13.6 billion years old. Yet the supermassive black hole found at our galaxy's core, Sagittarius A star, is only 4 million solar masses. The Andromeda galaxy's supermassive black hole, while bigger, is still only 200 million solar masses. One of the big factors to consider here is the difficulty in detecting and measuring black holes. This is still a really new field of research, as technology has only just allowed us to start observing black holes in the last few decades. Even then, we can often only observe the area surrounding black holes, that is, before the Event Horizon Telescope came along. But even that telescope takes ages to image just one black hole, so our general understanding really is still quite limited. In fact, most of the distant black holes we know about can only be seen because they are quasars. TON 618 is a quasar. Matter is pouring into the black hole's accretion disk at an incredible rate, and because of this, it's erupted into a quasar. Quasars can only be sustained as long as matter is falling into them, otherwise they revert back to dark black holes. It's hard to fully grasp the physics of the accretion disk, but it is believed that the friction here is so great, the accretion disk of a quasar by itself can produce thousands of times more light than entire galaxies combined. TON 618 produces as much light as 140 trillion suns, completely outshining the galaxy it resides in to the point that we can't even see it from our perspective. However, because quasars are the brightest objects in the universe, they can be seen from very far away. So, one reason for large black holes being far away is down to something known as Malmquist bias. This is where brighter objects further away appear more plentiful, when in reality, we simply can't see the dimmer objects at that distance, implying there may be an argument that the largest supermassive black holes are actually distributed fairly evenly throughout the universe. If a galaxy has a very large black hole but it's not a quasar, it means we won't see it after a certain distance because a galaxy is much dimmer than a quasar. Another reason why we don't see the biggest black holes close to us is due to the nature of the universe itself shortly after the Big Bang. As you may know, the universe is ever expanding, and during the early universe, matter was a lot closer together. Quasars were more common back then because they need extreme amounts of matter falling into them to give off light, and there was a lot more gas around during the early stages of the universe. Not only has the universe expanded, but over time, gas gets converted into stars. Some of the largest types of stars eventually turn into neutron stars and black holes themselves, meaning that they never get recycled back into gas. Less available gas means less gas will fall into a supermassive black hole. One of the theories for the fate of the universe is actually based on this, called the Big Freeze, where after some trillions of years, all the gas in the universe is eventually converted into black holes. Even now, we see some galaxies where their gas has been completely used up, meaning no new stars can form. These are called elliptical galaxies. Spiral galaxies still have gas and dust structures, and thus can still produce new stars. It is interesting that most of the largest supermassive black holes appear to be in elliptical galaxies where there is no gas left. Gas needs to lose momentum to fall into the galaxy's central supermassive black hole, and if that happened, then the supermassive black hole is likely to be much bigger because of all the infalling matter. With elliptical galaxies, this has already happened, whereas with spiral galaxies, this hasn't happened to the same extent. One such trigger for gas losing angular momentum could be the gravitational influence of nearby galaxies, or even collisions with other galaxies. In addition, there is less gas available in the universe now than there was during the early universe, so black hole growth probably occurred rapidly then, but has slowed down now. This might be why there is no quasar within 500 million light years of us. As the universe ages and things become less chaotic and more spread out, the number of active quasars has decreased, which means the only quasars we see, some of which are the largest black holes we know of, are the ones that happened a long time ago. So, why are the largest supermassive black holes often the youngest? Well, although it may appear that way, it might not actually be the case at all. We can measure distant bright quasars simply because we can see them. Older and closer black holes may also be large, but because of Malmquist bias, we haven't found them yet. As studies continue and technology improves, we'll start to get a more complete picture of the universe around us. With the James Webb Space Telescope nearing its launch, I felt like it would be a good idea to have another look at some of the remarkable images of its predecessor, the Hubble Space Telescope. Hubble has been in space for 30 years now and has increased our understanding of the universe drastically during this time. A type of object Hubble has observed is galaxies. Galaxies, as we've seen earlier in this series, come in all different shapes and sizes, with star populations ranging from millions to the trillions. They are fascinating, beautiful objects, each containing its own story of how they formed the way they did, let alone the tantalizing question about the possibility of life somewhere in them. While we have only observed the tiniest fraction of the total number of galaxies in the observable universe up close, did you know that Hubble has seen galaxies all the way through their evolution, from galaxies in the throes of starbirth or starburst, to galaxies that are inert, anemic, or dying? I'm Alex McColgan and you're watching Astrum, and today I wanted to look through this spectrum of galaxy evolution, focusing today on the ghostly, beautiful remnants of galaxies that are on their way out. I hope by the end of this video to have earned your like and subscription. When looking at a galaxy, the first indicator of the stage of its evolution is to look at its shape. It is generally believed that spiral and barred galaxies are some of the least evolved galaxies in the universe, whereas elliptical galaxies are the most evolved. That doesn't necessarily mean spiral and bar galaxies are younger though, it's just that they take longer to evolve. Here's an example. Number 68 NGC 2336. Galaxies with spirals consist of flat disks, where stars mainly orbit in the same direction. One of their defining characteristics are the arms that extend from the galaxy's center. These arms can spiral out directly from the galaxy's core, or sometimes the spirals come from a bar. They consist of a concentration of stars, gas and dust. Galaxies that have an abundance of dust are likely not as far along the evolution process as less dusty galaxies, as this dust has yet to be turned into new stars. Should no outside influence accelerate the dust consumption, a galaxy like this may produce stars at a fairly slow but steady rate for billions of years yet. How do we know it's not producing stars very quickly? Well, a distinct feature about this galaxy is the lack of red H2 regions, or stellar nurseries. Instead, while star formation is clearly still taking place due to all the bright blue stars you can see in this image, it will remain as a spiral galaxy for a lot longer than a galaxy bright with H2 regions. Like number 69, NGC 972. Wow, what a pretty galaxy. It almost looks like it's ablaze with all the activity happening around it. When a galaxy is so red, we characterize it as a starburst galaxy. That is to say, star formation is happening at an incredible rate. These red regions are the H2 regions the previous galaxy was missing an abundance of. As starburst continues, it will quickly use up the gas and dust structures you see here, converting it all to stars. Also, notice the blue glow like a halo around the galaxy. The blue hue comes from blue stars, the hottest and most massive star type. This is another indicator of rapid star formation, as these stars require huge amounts of matter to fall into them during their formation. Number 70, Messier 61. Another incredible example of a starburst galaxy is M61. M61 is a fantastic galaxy for observation because it's angled almost exactly face onto us. This means all the dust lanes and its red nebulae can be studied in detail. That's a lot harder to do with a galaxy that's edge on. Looking closely at the center of the galaxy shows a neat symmetry with the dust lanes. However, the further out you zoom, the more you notice how it becomes less symmetrical. This arm seems to split into three, whereas this one retains its structure. Usually an asymmetrical galaxy indicates that it is being perturbed in some way, either from the gravitational influence of a nearby galaxy or from an actual collision with one. In this case, M61 is actually found 50 million light years away in the heart of the Virgo cluster, surrounded by over 1,000 galaxies. It's this outside influence that likely causes starbursts to happen and for a galaxy to accelerate its evolution, as this outside tug of gravity causes the dust clouds within the galaxy to collapse in on themselves, creating stars. Number 71, NGC 4921. All galaxies will eventually exhaust their supply of gas and dust as they get converted to stars and then neutron stars or black holes. A small percentage of gas and dust also gets consumed by the supermassive black hole believed to exist at the center of every sizable galaxy. What happens to a galaxy then? Well, NGC 4921 is a good example of a galaxy about to transition into what is known as a lenticular galaxy. However, this one still has its spiral arms visible, so it remains classified as a spiral galaxy for now. It seems that star formation and dust lanes are a key element of keeping the shape of a spiral galaxy's arms, and when this process stops and the material runs out, the arms seem to lose some of their shape and definition. The color of the galaxy also changes to a ghostly white or reddish white as the galaxy's blue star population burns out and disappears. This is a fascinating galaxy. It is really unusual to see a spiral galaxy so devoid of color. The only colors visible really are the few remaining blue stars clinging to the dust lanes. Astronomers have described this galaxy as anemic, as star formation here must be incredibly slow. Number 72, NGC 2217. This is the first true lenticular galaxy I've shown you today, although NGC 2217 isn't totally done with star formation just yet. Notice the blue stars around the outer edge of the galaxy. However, in this instance, the dust here is almost completely exhausted, and the spiral arms have lost their definition. The bulge at the center of the galaxy has a white and reddish hue, showing that only older and less massive star types exist here. There are no blue stars visible to speak of. Number 73, PGC 10922. Here's another face-on galaxy for you. This particular lenticular galaxy is further along its evolution again. Most of the galaxy here is completely devoid of gas and dust, apart from towards the center. You'll also notice how any arms that once existed have been totally wound up until they are almost indistinguishable. All that's left really are old stars and a flat disk, but even the disk will eventually lose its shape as the galaxy widens and evolves into an elliptical galaxy. Like what is happening with number 74, NGC 1947. With this lenticular galaxy, we can still see the wispy remnants of the spiral arms. However, the stars in this galaxy have clearly already stopped orbiting along a flat disk, and now simply orbit slowly and from all directions. The very last stages of a lenticular galaxy look something like NGC 1533. There's no gas or dust noticeable. However, you can just about see the remains of a bar structure coming away from the core, indicating that this was once a barred spiral galaxy. Eventually, what you end up with is something like number 76, Messier 105. This is a true elliptical galaxy, a galaxy almost totally devoid of gas and dust. This galaxy is so anemic that only one sun-like star gets produced in a galaxy like this every 10,000 years. So what you are left with is the vast majority of the stars found in this galaxy being older, redder star types. If we really zoom into this image, you can see the red sprinkling of stars, especially as we move away from the brightness of the galaxy's core. This is the last stage of a galaxy's evolution that we can observe. These stars will last for billions to trillions of years, and the universe is too young to see what happens eventually to a galaxy like this, although it is thought that they will simply become dimmer and dimmer as one by one the stars reach the end of their lives. So there we have it, a snapshot of the evolution of galaxies. While having an almost spooky vibe to them, I really like lenticular galaxies. Their unstable nature produces some amazing patterns that you can't find in any other galaxy type, although it is somewhat sad to think too that as the universe ages, spiral galaxies will become less and less common, until the only galaxy type remaining are the elliptical galaxies. Hubble has released a zip file on their website containing the top 100 pictures Hubble has ever taken. What I will do over the course of this series is go through these pictures one by one and explain what it is you're looking at. And believe me, some of these pictures require an explanation. Episode 4. For the episode playlist, click on the annotation here or have a look in the description. Number 22, NGC 4449. At first glance, I thought this was one of the Magellanic Clouds, but it's actually a small, irregular galaxy in a galaxy group called Keens Venatici, about 12 million light years away. This means, like us, it is part of the Virgo supercluster, otherwise known as the local supercluster of galaxies. It is similar to the Large Magellanic Cloud in that it has a general bar shape, but the big difference is this is considered a starburst galaxy. It is very active in producing new stars, as can be seen here in these pinkish regions. Pink or red areas in a galaxy are generally a telltale sign of star formation, as stars surrounded by hydrogen gas ionize the hydrogen to glow red with intense radiation. Another telltale sign of high rates of star formation is the many blue stars you see in this picture. Blue stars are extremely hot, young, and often massive stars that will burn out quickly because they get through their fuel so fast. Because these stars can only live to a certain age, they must have only been produced within the last few million years. And as we can see, there are many blue star clusters in this galaxy. This starburst is thought to be because of galaxies interacting with NGC 4449. If we zoom out a bit, we can see this trail of red stars, perhaps the remains of a spheroid galaxy passing through NGC 4449, and it's stretched by this tidal effect. Looking at the galaxy center, we see a bright white group of stars with some dark clouds of dust around it. Stars can form within clouds like these. This galaxy is 19,000 light years across. Number 23, HD 97950. This spectacular superstar cluster is found within NGC 3603, an H2 nebula. It is incredibly pretty and has been studied a lot because it's found in the Carina spiral arm of the Milky Way, roughly 20,000 light years away. NGC 3630 is interesting to astronomers because it is the most massive visible cloud of glowing gas and plasma, known as an H2 region, in the Milky Way, and the superstar cluster has the densest concentration of stars known in our galaxy. The UV radiation and stellar winds have carved into this surrounding dust, producing these beautiful shapes, but also giving us an unobscured view of the superstar cluster. Stars of note in this cluster are Cher 25, a star 60 times the mass of our Sun and reaching the end of its life cycle. It's expected to go supernova any time now, as it's already thrown off matter in a similar manner to what has been seen in other supernovae. We also have the three main stars in the heart of the cluster, barely distinguishable in the center of these images here. All three are Wolf-Rayet stars, each about 100 times the mass of the Sun and millions of times more luminous. Two of them are incredibly close together as part of a binary star system, taking only 3.5 days to orbit one another. This means they are practically touching, no doubt exchanging a lot of mass, as well as having an incredible tidal influence on each other. Zooming out a bit, we see that visually, NGC 3630 is right next to another nebula, NGC 3576. In actual fact, this other nebula is much closer, only about half the distance to us. They just so happen to be visually aligned. Number 24, Messier 74. On first glance at this image, I thought it was another viewpoint on the famous galaxy we've already looked at, the Whirlpool Galaxy. And putting them side by side, these galaxies do look remarkably similar. They are both grand designed spiral galaxies for a start, and have similar dust patterns weaving through their arms. But putting them side by side, you can tell that there are slight variations in these two galaxies. M74's arms are lined with hot blue stars, with pink and red star forming regions dotted all over. You may think the arms of galaxies like this are static arms rotating around the nucleus of the galaxy, but actually they are the visual effect of density waves. As gas and dust orbits the galaxy, they pass through the galaxy's density waves, which compresses the gas and dust and causes stars to form. Existing orbiting stars also clump up in these density waves. A lot of these stars will be blue and only short-lived, perhaps completing their life cycle in only a few million years. M74 is about 32 million light years away and has a low surface brightness, making it one of the most difficult Messier objects for amateur astronomers to observe, and giving it the nickname the Phantom Galaxy. It is probably just a little smaller than our own Milky Way galaxy, containing about 100 billion stars and being 95,000 light years across. It sits in the M74 group, a small, little remote group of galaxies. Number 25, ARP 148. So, first impressions, what do you think this could be? Pause the video and take a guess in the comments if you want. Well, this bizarre shape, found a staggering 500 million light years away, is a galaxy and is nicknamed Male's Object. It is in fact most likely to be two merging galaxies, the initial collision theorized to have created a shock wave which drew matter into the center before it propagated out into this ring you see. The tail is a streamer of stars from one of the galaxies, further suggesting this is an ongoing collision. Interestingly, and on a little side note, the ARP catalogue is the Atlas of Peculiar Galaxies. Number 26, Able 2218. Now if you thought the last image was an impressive distance away, have a look at this one. Able 2218 is an impressive cluster of galaxies 2.1 billion light years away. Clusters like these are particularly scientifically interesting because these galaxies' immense gravity bends the light around them, acting as a magnifying glass to see galaxies even further behind them. These long arcs you see in the image are actually distant galaxies' light, stretched and warped by the gravity of the nearer galaxy cluster. In this image is perhaps the most distant galaxy known at an estimated 13 billion light years away. In this image it's barely visible, but in an enhanced version we can make out its stretched appearance. Because of this lensing effect, the galaxy appears twice in this image, here as well as here. We see it from Earth as it was only 750 million years after the Big Bang, meaning we're looking back in time to really the early universe. There are around 10,000 galaxies in this image. Number 27, Able 1703. This is another galaxy cluster, doing the same lensing effect we looked at in the previous image. I want to explain in a little more detail about how this lensing effect works. Firstly, we look at a distant, massive object. Gravity is theorized to warp space-time, perhaps a topic I'll come to in another video. But often, elliptical galaxies are the biggest galaxies in existence, and the more massive the galaxy, the bigger the warping effect on space-time. You can see this with the lensing effect around the big elliptical galaxy in the middle of this image. As space-time is warped, light is bent around the galaxy, and if it's aligned right, it gives us a magnified view of the other side of the galaxy. It's a natural, handy magnifying glass just floating in space. And about this galaxy cluster, Able 1703 is around 3 billion light years away. Space can be beautiful. You have flawless elliptical galaxies with no traces of dust bands blocking the view of their stunning shape. You have grand galaxies with spiral arms that wrap around the entire galaxy with a surprising level of symmetricity. And then you have the ARP catalogue, or the Atlas of Peculiar Galaxies. These are galaxies which laugh in the face of order, galaxies which are often going through a very tumultuous time in their existence, and they are fantastic in their own right, each with a story to tell. I'm McColgan and you're watching Astrum, and in this Hubble episode we will go through some of the most peculiar galaxies that Hubble has ever seen, and I'll try and explain what it is you are looking at. Number 43, ARP 116, or Messier 60. At first glance, this galaxy doesn't look so unusual. It seems like a standard elliptical galaxy, a massive galaxy which has already used up most of its dust and gas in creating stars, which gives it this smooth appearance. It can be found 57 million light years away and has one of the biggest black holes ever discovered near its center at roughly 4.5 billion solar masses. But this isn't particularly peculiar so far. Zooming out a bit reveals something very unusual. M60 is right next to another, very different looking spiral galaxy called NGC 4647. From our viewpoint, it looks like the galaxies should be interacting with each other, but there aren't any immediate signs of this. This is very unusual, to see two galaxies so close, but without any warping of their shape. As it turns out, they are not side by side, but rather one is in front of the other. There's one other really unique thing in this image, another galaxy you probably haven't noticed. This tiny little galaxy here is known as M60 UCD1. It is the most densely packed galaxy that we know of. Being only 300 light years across, but having 200 million solar masses contained within it. Towards the center of this tiny galaxy, stars are so densely packed, it makes the density of stars about 15,000 times greater than found in Earth's neighborhood in the Milky Way, meaning that the stars are about 25 times closer together. An X-ray view of the surrounding area from the Chandra telescope reveals all the black holes and neutron stars found in Messier 60. And as you can see, this tiny galaxy also has an X-ray source, indicating there is also a black hole to be found at the center. Scientists believe that this is a black hole with roughly 10 million solar masses, which would make it just a bit bigger than the black hole found at the center of our Milky Way galaxy. If this is the case, it is thought that this galaxy used to be much bigger, but most of its mass was stripped away, leaving just this dense cluster of stars found near the center. Number 44, ARP 147 or IC 298. You don't have to look too closely at this image to determine that this is a very weird looking galaxy. It is in fact a pair of galaxies that have collided, found roughly 440 million light years away. This is what the previous galaxies could end up looking like if they ever collide, because the left galaxy is an elliptical galaxy and the one on the right is a spiral galaxy. The collision, estimated to have happened 40 million years ago, caused the spiral galaxy to undergo extreme star formation, seen in the bright blue regions. The most active time of star formation, or starburst, was 15 million years ago, and would have produced the most massive types of stars. But due to these stars being short-lived, lasting only tens of millions of years, most of the biggest ones have already died as exploding supernova and become either neutron stars or black holes. This reddish part of the ring appears to be the original nucleus of the galaxy, now just a segment of the ring. Due to elliptical galaxies having exhausted most of their supply of dust and gas, star formation isn't nearly as prevalent in this galaxy. What you can see though is the effect of tidal forces causing a ripple or a shock wave through the galaxy, which you can see as the stars have clumped into rings. Number 45, ARP 77 or NGC 1097. Another galaxy with a smaller galaxy tucked away inside it is NGC 1097. Unfortunately, the Hubble image cuts the smaller galaxy out, but ESO's Very Large Telescope has also had a look at the galaxies, in which you can see its smaller neighbor, NGC 1097A, a small elliptical galaxy that is in orbit around the bigger galaxy. NGC 1097 itself looks quite like a giant eyeball to me, with its pupil surrounded by a bright iris. Zooming in on the iris, we can see that it is a ring rich in star-forming regions. Each of the bright blobs are thought to be hot bubbles of hydrogen in which stars are forming. Viewing different wavelengths of light shows that some dust from the rings is also being sucked in towards the supermassive black hole found in the galaxy center. But this isn't the most peculiar thing about NGC 1097. Zooming all the way out reveals 4 jets emanating from the core of the galaxy in an X shape. Due to the lack of hydrogen gas found in these jets, scientists believe that they are the remains of a small galaxy that NGC 1097 cannibalized. Number 46, ARP 142. Here is another galaxy merger that kind of looks like a penguin and an egg. When viewed like this image might seem serene almost. But in fact, the biggest spiral galaxy has taken a beating from this merger. This long section here is where one of the spiral arms of the galaxy has been ripped away by the elliptical galaxy, which doesn't look like it's too phased by this collision, other than the fact that it looks quite oblong in shape. Again, the blue regions along the edges here contain starburst, and this 3D view shows that these dust lanes are probably becoming detached from the galaxy too. These galaxies are found roughly 350 million light years away. Number 47, ARP 210 or NGC 1569. Now, I don't think you've seen a galaxy quite like this one. Well, that's because this tiny galaxy, no bigger than the large Magellanic Cloud orbiting our Milky Way galaxy, is pretty much just one giant nebula. This galaxy is almost the total opposite of an elliptical galaxy, as it is rich in gas and dust that does not yet form stars. NGC 1569 is found near the Maffei group of galaxies, and due to its close proximity to these much bigger companions, the gas and dust within it has recently been compressed, causing rapid starburst at a rate 100 times faster than anything observed in our own Milky Way. Towards the center are densely packed, massive stars, which have blasted away the red dust and gas towards the outskirts of the galaxy through solar wind and supernova explosions, leaving behind huge star clusters. The small white stars found in the halo of the galaxy are older stars which have been around for much longer. We can have such a detailed look at this galaxy because, although it is small, no bigger than 6,000 light years across, it is also reasonably close to us at only 11 million light years away. Number 48, ARP 272. We'll finish with one more galaxy merger seen from a rather interesting angle. These two galaxies are roughly the same size and are just astronomical moments away from impacting each other. There's also a third galaxy found just above them, which is also in on the action. The reason for seeing three galaxies merging at the same time could be due to the fact this is happening in the Hercules supercluster, roughly 500 million light years away, which is one of the biggest filamentary structures of galaxies that we know about in the universe. You see, the observable universe, as far as we can tell, kind of looks like a giant web, where galaxies band together to form these filaments, which form the boundaries between large voids in the universe. This is what the universe up to 500 million light years from us looks like. And even in this space, you can see this banding of galaxies. And just because some of you have asked about this in the past, this is where Boötes void is, which is one of the biggest voids of galaxies that we know about. Thanks for watching. Making this video required some long-term planning and work, which we were only able to do thanks to the consistency and sustainability of your memberships as Astronauts on Patreon. A huge thank you to everyone who has signed up, and if you'd like us to make more videos like this, you can join with the link down below. When you join, you'll be able to watch the whole video ad-free, see your name in the credits, and submit questions to our team. Meanwhile, click the link to this playlist for more Astrum content. I'll see you next time.